image captioning with embedding reward. And this was presented in CVPR 17, and I'll be talking about it today. So here's a bit of the outline. I have a brief introduction to image captioning, the past works, the motivation for this paper, the contributions, which include reinforcement learning, training, local head inference, finally evaluation, then conclusion. So let's start with image captioning. So what the authors say image captioning is in understanding the image content and the diverse ways of describing it in natural language. So it seems all very fancy, but what does it mean really? So it's actually very simple. It just means that we have an image and we want to turn it into some words to describe the image. So for this image, let's say, it can be described as a group of people running in the rain. But this is only one of the many captions, and there can be many captions describing this image. So let's formulate this problem. So we have an image I, and we want to generate a sentence S. And in a sentence, there's a group of words, W1 to WT. And W1 equals to the first word, which is A, and WT equals to the last word, which is rain. So, yeah, it's simple. So why do we really need image captioning? So there's an underlying technique that can be used for image classification and clustering, and it can be used in image retrieval for search engine recommendation. So let's say you type in some words, you can find images. So the techniques can be used for this as well. And finally, accessibility for the visually impaired. So what does this mean? So when they walk around, they can actually understand stuff around them, because the computer can help them to convert the images they see into speech, which the visually impaired can understand. So we'll talk about a summary of past works. This is not going to be long, but a very short one. So in the past works, there have been many works that manipulate the RNN. And one of these work is the deep captioning with multimodal retrieval, recurrent neural network. So we see here as a simple RNN network, which should generate the caption. But what they have done is to include the context, which takes the output of the recurrent network and join it with the embedding and also the image to give some context to output the sentence. So this is one of the many works which have done to manipulate RNNs. So another way to improve the accuracy in the past works is attention, both in the spatial attention and also the semantic attention. And one of this work is by this, which is the show and tell neural image caption generation with visual attention. So what they've done is they look at different parts of the image and they come up with words to describe the image. So this uses attention. So now this is a totally new branch of image captioning, and it's a novel way of doing it by using reinforcement learning. And I think, as far as I know, it's the first one to use it in image captioning. So what is the motivation behind using reinforcement learning? So the problem with the past techniques are that encoder and decoder networks use greedy or beam search, which means misses good words in the early steps. So let's say using greedy, we always pick the top words from the RNN, and maybe you take a lying on the chair, but we don't get holding a baseball bat. So greedy search might work or might not work depending on the image. A bit better than greedy search is the beam search, which takes a width and a top K. So let's say we want a width of 1 and top 3. So what does this do is you find the next word, so width 1, the next word, and find the best score, the words with the best score, and pick the top 3. So let's say there's lying beside, lying on, sitting beside, eating A, and eating that. So we're going to take the top 3, one which is lying beside, lying on, and sitting on, and do this iteratively to collect the best sentence. Of course, this doesn't take account all the possibilities. So this is something that we want to improve on using reinforcement learning. So why reinforcement learning? So once again, it does not only do greedy, it has ability to make decisions and navigate the path and do some path planning. And reinforcement learning is able to see long term. It's able to execute a set of actions that finally gives the highest cumulative reward. For the sentence. So how do we use reinforcement learning? we make use of an agent, a policy network, and a value network. So at each stage, in time t, the agent is given the image and the predicted words so far. So let's say in the previous image, the one the people are running. So let's say some people are running. So maybe I give some people. So the network has to predict R, something like that. So that's the state, some people and the image. And then the agent takes the action to predict the next word, which is also set of words. One word from the vocabulary Y. So let's talk a bit of the policy network. The policy network is the one that models the probability for the action at the current state. So it's the one that is with the short term. It wants to see the short term reward. And this is the standard encoder-decoder network, consisting of an CNN with the structure of VGG16 and an LSTM with 512 dimensions of input and hidden layer. And how we do this is we take the image, we pass it to encode it with a CNN, and then we decode it with a RNN to generate a sentence for this image. So this is the standard things that you see image captioning right now. And now we talk about value network, which is the interesting part, because this value network predicts the total reward or the final reward, expected final reward given the current state and the policy it is using. So we can approximate this value network given a certain policy with V-data, and we use a CNN, LSTM, and a fully connected layer to model this. So how do we do it? We take an image, we encode it with a CNN, we take an RNN, we encode some text, and then we concatenate it and we output a scalar reward using the fully connected layer to generate the expected final reward for this sentence, for this current state given this policy. So that's the value network. But the interesting thing about value network is that it requires a concrete reward for training. Because right now we have the image, we have the sentence, the ground truth of it, but we don't have the reward. So how do we generate the reward? We use something called visual semantic embeddings. And this maps the image and the text into a single space, and then we can find the similarity within that space. So how do we do it? So we use this technique, and this technique consists of an RN, which is basically a GRU with 300 dimensions and hidden layer of 1024. CNN, again, VGG16, and a function FE that takes in the image and map it to the embedding space. So how do we do this? So we have image, we have a mapping function, we have a single space, and we have the RNN to map it to the space as well. And how do we train this network? So we train this network by fixing the RNN weights, and we train only the mapping function and the RNN. So then we use a bidirectional ranking loss to train this network, to map it into the same space with the text and the images that are similar, close to each other. Yeah. Any questions as of now? Okay.
So this size is going to map one phrase into one point in the embedding space?
Yes, one sentence into one point in the embedding space.
And what do we expect to see?
We expect to see images. So let's say we have an image dog on a bench. So we expect a dog on a bench to be close to this image in the same space, and we expect to see like a dog on a building or a dog on the street to be further away in that space. So we want to know. We want to ultimately find the distance, which is the reward, the similarity between the two things, which is the image and the sentence.
So supposedly, like the phrase a dog and a dog sits on earth, which one is should be closer to the image?
Okay, so a dog sits on earth is highly correlated in the space.
Yeah.
So they are actually very close to each other in this space. Yeah. So I'll talk about this a bit later. Next one, I think, during the training of this. So. Oh yeah, okay, so yes, that's right. It will be very close to the thing. So both will be very close to the same one. Yeah. So whenever there's a dog will be close. Yeah. So later when we train the value network, there's they will say there's high correlation between these two in the same space. Yeah. High similarity as well. Okay, so we talk about training the policy and the value network now. This is also a contribution because it hasn't been done in this form. So we do some independent training first. So we independently train the policy network using supervised learning with the inputs a state and also the action. So let's say the dog. So let's say the image of the dog sitting on the bench. So a dog sitting, and then we have the next action on. So this is how we train the policy network. And we minimize the cross entropy loss given by this formula. So we do the same training with the value network as well, using supervised learning, and with the input a state and also a reward. But this state is special because we randomly select the states and we don't select the states from the same sentence because these states are highly correlated. So because the rewards are highly correlated as well. So we don't select them. If not, you will overfit this model. So we select we select a states from each sentence, and then we train it with the reward that is generated by the visual semantic embeddings. And this is the formula to calculate the reward from the visual semantic embedding. And then we use mean square loss. So this is the output of our value network, and this is the R from the semantic embedding. So we want it to be as close as possible to that. So then finally we have joint training. So we jointly optimize the policy network and the value network. So let's say we have large capital theta, which takes in all the parameter of the value network and the policy network. And we have to maximize j theta to maximize the reward, expected reward. So the thing is, since in reinforcement learning, the reward only comes at the end of the sentence. So let's say a dog, there's no reward, but a dog sitting on a bench, then the reward comes. So at every point in time before the full sentence, there is zero reward, and there's only a reward at the end of sentence. That's why we can say that we maximize J, expected reward R, because the reward is only the one at the end of the sentence. Yeah. So this is the same as this. And in maximize J is non-trivial, so they use some theories from reinforcement learning to approximate the gradient, and the gradient is this, which we will optimize. So the last contribution is the look ahead inference. So what does this mean is we have both. Now we have the policy network, which is short-sighted, and we have the value network that's long-sighted. So how do we put this together to generate a good inference for the next word? So at each time step t, we have finite possibility of sequences. So let's say a dog, there's finite possibility of sequence that can come after. So it's able to take in all the possible sequence, and each sequence is a set of words that from 1 to t, the end of the sequence. Yeah. So this policy and value network can consider all this sequence from this state to the end. Yeah. So how do we score this? So we score the next state in line with the sum of the probability score of the current position, the policy score given the action taken for the next state, for the current state, and also the value score for the action taken from the current state. So it's basically a trade-off between these three. Yeah, which gives the inference. So what I mean by this is we could possibly choose some word with a lower probability from the policy network, but we maximize the overall total reward at the end. So let's say the action, the policy network say, oh, lying is a good word, sitting is good, eating is a good word, but holding is not such a good word. So then the value network says, oh, the combination of this will give holding the best cumulative reward at the end. Yeah, because holding gives a baseball bat, but lying there doesn't give a baseball bat. So this is the best sentence for this image, best possible path for this image. So that's the look ahead. So we have some experiments, and these experiments evaluate on Microsoft Coco, which is a caption evaluation tool. It has the image set split into 82,783, which is for training, 5,000 for validation, and 5,000 for testing. So this is standard for the past papers as well, so to keep it consistent. And each image is has at least 5 different captions generated by AMT workers. So basically people there typing captions. Yep. And the results is that this model outperforms even models trained with external data. So the one with the asterisks are the one trained with external data. So they train with like let's say social network data. So people type captions into images. So they train with that as well with the image provided with Microsoft Coco. And this actually performs better overall, mostly on most tasks. Yeah. So some analysis here. So to analyze which part of this whole framework produced the most results, or which part contributes to the end result, we use a few things. We have SL, which is supervised learning. So we use the only supervised learning model. We have SL embed, which use the supervised learning model with the embeddings. And we have SL raw VN, which use the supervised learning of the policy network with the value network that is trained without the joint training. Yeah. And you can see that actually most of the contribution most of the contribution comes from the value network. Yeah, because we can see that the score difference between the value network and SL is greater than the embedding from the baseline of SL. Yeah, but both actually contribute in the end because the full model is much higher than the two modules individually. Yeah. Okay, so here are some of the results. On the left 3 columns are those that are correct, and the last one is something that have gone wrong. So you can see that a man holding a snowboard next to a man in a scary costume. So the full framework produces a woman sitting on the ledge holding a snowboard, which is not too bad. And the supervised learning model gives a woman standing in the living room holding a Wii controller. So it totally misses out on the snowboard. So the good thing about the value network is it can find words that are not so high in probability but gives good results at the end. So yeah. So but the problem is like a man driving side by side on motorcycles, so a man riding on the back of a motorcycle. It's not too bad, but it doesn't capture the what the authors want or what the dataset wants. So the ground truth. But it does create some okay captions. Yeah. So finally, I want to conclude with the contributions of this paper. So there is a novel decision framework for image captioning using reinforcement learning, and the novel use of visual semantic embeddings rewards for training, and also the use of policy and value networks as global and local guidance respectively. So short-sighted and long-sighted. And in the future works, we can always change the policy network with something better. So we can include spatial and semantic attention, like in the past papers, into the policy network. And also, we can try other embeddings as a reward for the value network. So now I've come to the end, and